wind speed stochastic models case study for the Mediterranean area.
Yes.
Please. Oh. Any problem?
Nothing. Good afternoon. My name is Davide Gurrera. I work at the Applied Physics Department, University of Palermo. I'm going to introduce for you our last results concerning wind speed modeling and forecasting. This figure shows you an important result achieved by the environment at the end of 2008. In fact, for the first time, wind power technology has been ahead of any other power technology, and this is important also because at the end of the same year, the 27 European states unanimously agreed on legislation to achieve by 2020 the 20% renewable energy target. For this reason, the European Commission expects wind energy share to increase from about 4% in 2008 to 12% by 2020. As for the already installed wind power capacity at the end of the same year, Italy holds an important position in the world. In fact, it is preceded only by the United States of America, Germany, Spain, China, India, but Italy comes before important countries such as France, the United Kingdom, Denmark, Portugal, and the rest of the world. So, one of the main challenges faced by wind energy-based electricity producers is represented by wind speed fluctuations. In fact, second-to-second or minute-to-minute variations in wind energy production are a rare problem for installing wind power in a grid. But wind energy production may, however, vary from hour to hour, just as demand from electricity customers will vary from hour to hour. In both cases, other generators on the grid have to provide power at short notice to balance supply and demand. And the cost of providing this balancing service depends both on the type of other available generating equipment and on the predictability of the variation in the net electricity demand. On the spot market, demand and supply bids have to be submitted typically 48 hours in advance. And by equalizing demand and supply, the spot prices are found for a 24-hour period. This is an important period because our models are able to predict for 24 hours ahead for this reason. If forecast production and actual demand are not in balance, the balancing market has to be activated. This is especially important for wind-based power producers because of the aforementioned wind speed fluctuations. Experience from different countries, especially Germany, Spain and Ireland, has shown that the accuracy of the forecast can be improved in several ways, ranging from improvements in meteorological data supply to the use of a combination of different methods in the prediction process. Okay, the idea of using a mathematical model to predict the behavior of physical phenomena is well established. We know very well fluid dynamical models have reached a great degree of accuracy. But up to now, they can't solve completely the problem because of the great complexity of the addressed phenomenon. In fact, sometimes it is possible to derive a deterministic model, and sometimes it is not. In many problems, we have to consider a time-dependent phenomenon in which there are many unknown factors, or large experimental resources needed to produce a deterministic model are not available. In such cases, it may be possible to derive a stochastic model. The figure shows you a time series, an example, one of the hundreds of time series we have analyzed for our work. Our target is to forecast that series for a 24-hour period. You see, it is not simple to reproduce or to understand that behavior. Assuming a stochastic data generating process An observed time series like the one I'm showing you is regarded as a sample realization from an infinite population of such time series that could have been generated by the stochastic process. Although it may be possible to increase the sample size by varying the length of the observed time series, there will only be a single outcome of the investigated stochastic process, and time series analysis is essentially concerned with evaluating the properties of this underlying data generating process from the observed time series. Once a hypothetical probability model to represent the data has been set up, it may be used, for example, for simulation purposes, but also to draw useful inferences from the time series, like, for example, forecasting. Okay, the same time series is showed in this figure, but this time I made a radiograph because I want to know something more about it. Fundamental tools to interpret the properties of a time series are the sample spectrum at the bottom on the right and the autocorrelation function. It is quite evident, it is outstanding, a 24-hour period. It is a natural period for wind direction, wind speed, and other atmospheric phenomenon because of the sun period, 24 hours. So many time series contain a seasonal periodic component which repeats every S observations. We expect relationships to occur between adjacent observations and between observations separated by S units of time. And we take this into account by using a seasonal model. It is, at our best knowledge, it is the first time this kind of model has been proposed in the literature. And a SARIMA PDQ times capital PDQ subscript S process is defined by that equation. It is quite awful, but okay, if you know it, it's quite simple. It is important. B is the backward shift operator. Phi and theta are polynomials, and it is important for you to focus your attention at WT. It is an independent and identically distributed Gaussian noise. Our work is aimed at providing a general class of stochastic models for our average wind speed time series, taking into account all the main features of wind speed data, namely autocorrelation, non-Gaussian distribution, seasonal and diurnal non-stationarity, everything. The proposed approach for wind speed modeling and forecasting has been applied to the time series recorded from 2003 to 2006 in 29 sites of Sicily in Italy, at the meters above ground by the Servizio Informativo Agrometeorologico Siciliano. We focus now our attention, as for our results presented here, at sites number 4 and 1. They have been chosen because for convenience, for time sake, and they've been chosen because the two sites are quite distant from each other and present different features. Site number 4, Camarata, is near the center of Sicily, surrounded by the mountains, and site number 1 instead is situated in a more exposed area in front of the Mediterranean Sea. The spectral analysis, it is considering the whole data set, reveals the aforesaid 24-hour period. It is outstanding, so no comment. The frequency distribution instead reveals a fundamental property of wind speed data. Wind speed is not characterized by a Gaussian distribution. We have used two different models, a Weibull probability density function and a hybrid Weibull probability density function. It is not Gaussian, of course, sorry. So we need to pre-treat our data. Seasonal non-stationarity is removed by monthly stratification, and after such a stratification, the only residual periodicity is expected to be the daily cycle typical of wind speed on a land area. But the stochastic models employed in this study, the one we have seen in one of the previous slides, were rigorously developed for random variables possessing Gaussian distribution. A box cost transformation has been applied to the time series utilizing the present work, but in no case the transformer series passed the Shapiro-Wilk test for normality used in the literature. Hence, a new approach is presented here. The transformer series have the same diurnal cycle of the original data. The proposed approach attains stationarity by the use of a difference technique and employs seasonal models to allow for randomness in the daily cycle and to take into account the day-to-day correlation. This is the new transformation. You see the original data stand on the top of the figure. You see the skew distribution on the left. It is a Weibull distribution. It is well fitted by Weibull distribution. The sample spectrum on the right, there is a 24-hour period, and when we transform our data, we obtain a Gaussian distribution, more or less, and the same 24-hour period, as I said before. The new time series is obtained by solving the following equation for ZT. It is quite simple. The idea is quite simple because at the left-hand side of this equation we have got the Gaussian cumulative distribution function. V is the empirical non-Gaussian series. P is the series of the estimated empirical cumulative probabilities. That is to say, the probabilities of wind speed not to exceed V. Then we've got the mean, and sigma is the standard deviation of V. This is the class of models we propose, and the test on the right. The proposed class has proved adequate for 93% of the analyzed series. 93. Since it comes out that P is always minor than 2, it results that it is possible to model the investigated stochastic process, however after nonlinear transformation, by a suitable linear model with at most 10 parameters. But in some cases, just 3 parameters are sufficient. In the test, okay, there is no time. The developed automatic approach has provided satisfactory forecasts. Below we show the results for Camerata, A, at the top panel, and for Mazzarora. Poor prediction, more common during winter, are a consequence of sudden disturbances. You see, satisfactory prediction are characterized by points below the broken line. In the warmest months, we obtained the greatest number of points below the broken line, while in November, December, and January, we obtained the worst predictions because of sudden disturbances occurring in the forecast window. The same results, but with another indicator, because we used all in all we've used 4 different indicators of accuracy. The mean absolute scale error, the one we've seen in the previous slide, and here the mean absolute percentage error, but also we use the mean scale, the mean absolute error, and the mean root square error. This is one example of our forecasts obtained for Camerata. This is Camerata. And this is another example of forecast. The other that stand below the broken lines have got the same quality. And this is another example. Thank you.
Thank you very much. Questions? Thank you.
Thank you.
Dr. Ruggirello.